files and such. So we have with us Mario Kovac from University of Zagreb. Mario has been a long-time contributor of EPI, and his team, among other contributions, has been working on a floating point unit that is part of the RISC-V test chips that have been created within API. So Mario will give us an overview of that work and perhaps his perspective on next steps, etc. Thank you for being here, Mario. Take care.
Well, first of all, thank you all for surviving till the end of the day 2 and for this presentation. And of course, thanks for the invitation and this great organization of the event itself. I'm trying, because I know that we are a little bit behind the schedule, so I'll try to be concise. My talk today is not going to be general about EPI and all the things that the team has done. I will focus on one of the results of FER as one of the partners in the project itself. I'm going to talk about RISC-V floating point unit that we designed. So basically, we co-named it FAUST, and FAUST was the target of FAUST was basically to support efficiently support all of the vector floating point instructions in the RISC-V design that we had within EPI vector processor and the vector unit. So it has, I would say, 2 major advantages. First of all, it's compliant with IEEE 754/2019, which is the newest standard regarding the floating point computations, and it covers, of course, RISC-V 1.0 vector extensions. It's designed, well, we specifically optimized it as much as possible so that the actual design can be as beneficial as possible for our vector unit. So we have taken a lot of care about the area, about, of course, frequency. And one of the things that I will especially want to mention is some of the corner cases that are important for exact computation in that. It was integrated in 3 chips, as we heard earlier today in more extensive presentations, in EPAC 1.0 and 1.5. And it was, as we heard, also just sent out for tape out for the back chip. What are some of the features that we can say about it? It supports multiple floating point formats that are needed for today's computation. It has all of the required rounding modes. I would say rounding modes are quite tricky because they do take a significant amount of area if you want to implement them correctly. So we have seen a lot of designs that do not calculate things correctly when we come to some of those corner cases, and of course supports subnormal numbers. We are especially focused on possibility to customize the design. One special aspect of that was when we initially started to do that, and BSc was designing vector unit, and we were discussing in a vector unit, okay, how many pipeline stages we need in particular situations. So at one point it was decided, okay, we need 5 pipeline stages, but this is only one design. So if we want to use it in different configurations, we might need less or more pipeline stages. One interesting fact that we realized, and it was discussed, I would say, a number of times during the last 2 days, you cannot always trust the tools. So what we realized in certain times of our design is that we played around with pipeline stages a little bit, how to configure, where to position the registers, how to minimize the area and everything. And we realized that synthesis tools sometimes produced results that are, I would say, least to say weird, in the sense that, they kind of performed well from time to time. So sometimes even if you higher the frequency, design works better than with the lower frequency. Then you get sometimes area which is, you would expect to lower the area or, enhance the area because you make some changes, you get completely opposite results. And at that time, we realized that, we cannot, if we want to really deliver a unit that has, I would say, maximum capability with the lowest area or higher speeds, that we need to actually go deep, dig deeper, and try to find exactly what is happening in the actual synthesis. So we decided not to let the tool to synthesize everything, but we control certain parts of the design, especially pipelining. So one of the, I would say, key features is that right now we can really configure the design related to pipeline stages. So we can adapt the design to some future processors that might require more or less pipeline stages, or have different interfaces, or have different timings or whatever is needed, because we are more aware of what we can control and let the synthesis tool does the some I would say more predictable things. Also, what is quite important, what we did is we played with the way some of the computations are being actually executed. We know, from computer architecture that some of the computations can be done in various ways. Depending on that, we get different things, delays, throughputs, area. So we played with different algorithms just to know what can be best for certain scenarios. Also, for some of the designs, we know that we might have different lanes that support only certain operations, different lanes supporting less number of operations that needed. So FMA is usually critical. There are some other operations that are less used, so we might not include them in certain lanes. So we made the design quite configurable, and also the interface to the vector unit, we can adapt to whatever the needed interface is. Some of the operations, I don't want to read it. The FAUST supports all of the operations that are defined in the standard. So this is basically the list, and here is some of the basic diagram of our internal structure, where we can see some of the stages are pipelined, some of the stages like division square root, like iterative, so that we can basically save on some of the area in the design. Of course, we can get the results at a later time, but we save significantly on space. Arbitration and setup of data is also controlled, so we can modify it if needed for some other designs, like we have for the BSC vector unit. As a complement of the actual design, we were also in parallel working on the verification environment. The reason for that is that, while we were generating the design, we wanted to check that, the changes that we did, or the modification, or the design that we did is actually correct. So we started with something that is widely known, which is Berkeley SoftFloat C library. But, that library does not support all of the cases that are required for RISC-V vector computations. So we have extended that library with certain operations and certain corner cases that were not existing there. And we have also included some wrappers so that we can use it in the UVM-based environments. For that, we also created some of the random number generators that can basically test some of the cases and help us in basically evaluating the design and the operation. What we see here on this picture is device under test, which is a floating point unit. It can be FAUST. We use this for testing FAUST, but it can be used for any other floating point unit that is out there that wants to be verified against the specification that are needed to actually tape it out. We, of course, think that it was very significant for our development because using this and making some changes and having like a co-design type of approach helped us a lot in getting some design errors very early in the process. And of course, UVM environment itself is very much used in the industry, so it can be easily integrated in the industrial process of verification of the chip. We have also used system Verilog assertions for some of the things so that the whole environment is really very efficient. One thing that this is kind of first public information on our newest releases. So I wanted to use this opportunity of EPI event to announce some that we have worked also in parallel to even further improve the design of the floating point unit. So we have achieved significant area reduction with implementation of different algorithms for computations. Also with implementation of manual pipelining, where some of the things that we found in the initial phase were sort of disappeared when we introduced some of the manual pipelining methods. Also, we have been able to more closely control the handshaking of the interfaces between the floating point unit and the vector unit itself. And for today, as I said, this is the first public announcement. Some internal people know that, from the review meeting, but we have right now in the process of incorporation of our spin-off, which will be called Proactive Compute. That is going to, continue bringing this, to the market and to some of the commercial users. There is not that much information so far, but it's going to be once the legal process is over. But I encourage you to, if you have, of course, interest in using this in some of your future design, to follow us on our web pages. As one of the results of in the exploitation part of EPI, we are happy to say that we are, of course, offering right now the commercial licensing of both FAUST and FPUV. It's interesting, we wanted to find a good name for FPUV that would be attractive, but then realized that actually at the first we put it like FPU verification, like V is for verification. But then a lot of people that didn't know that said, oh, that's FAU5, like from RISC-V. So we said, well, why don't we keep it like this? Don't try to find some other good name. It's kind of like, we like it. So both of these will be, of course, available for evaluation and for, commercial licensing. And, I encourage any of you, or if you know someone who might be interested, to forward this information. And with that, I'm as I said, I'll try to be as short as possible. I would like, to conclude my presentation and have, of course, some mandatory slides about funding and EPI. And thank you so much.
Questions or comments for Mario? So Mario, about the verification environment, perhaps you can say that could be part of the licensed IP. Would you put it as bundle?
Yeah.
Yeah, not just.
I mean, it makes sense, because if you include our IP, we would of course give you the tools to verify it once you integrate it in some of the designs, and you can of course do it even without our designs. But it's I think valuable result that can be used.
Any other comment or question for Mario?
Thanks for the talk. So at the very first slides, you mentioned something about the synthesizing. Can you give us an example, of the weird things that you saw while synthesizing? Was it any, for example, retiming issues, that the tool placed the register back and forth or something like that?
Yeah, exactly. I mean, I can give you two examples. Well, first, for example, retiming issue, we played with number of stages, right? And when we played with number of stages, we start with, let's say, 2 pipeline stages, 3 and everything. Then at certain times, let's say with lower number of stages, we could not meet the frequency. With lower number of stages, we could meet the frequency. With high number of stages, we could not meet the frequency, and that was random. I mean, when I say random, one day it would work, the other day we would change something, it would not work. Second thing was, for example, we could see, and when we partially tested, some portions of design to see, what is the delay, the maximum delay through some logic. We could see that, it would meet, the target frequency, and then, it would kind of work. Then we would come to a certain frequency that was below target frequency. Then it wouldn't work. Then we would go above target frequency, and then it would work again. And I mean, I still don't know what is the reason for that. So I'm sorry. We tried. We tried to figure it out. We couldn't. Maybe if we had, I don't know, design engineers that designed those tools that were working with them for, I don't know, 10+ years, maybe they would know the reason. But whoever we talked to, they couldn't tell us, what could it be. But I think it was a good thing, because that forced us to go in this other direction. So, it's not bad.
The magic stuff of the synthesizer, we always face it.
Yeah, so it's and with that, I mean, you can place the initial register, you can say where to place the final one, but those in the middle, sometimes we could see it places them, all of them grouped like one after each other. It doesn't make any sense. So it's
okay. That's a quite interesting input. That there is sensitivity to tools for when we go for advanced designs. Any last comment or question from the people in the room or from the remote attendees? Well, if not, let's thank our speaker again.
Thank you.